Imagine, for a moment, an entire city humming with power, but not from coal plants or gas turbines. Imagine it powered by, well, huge towers of construction blocks, rising and falling, or maybe even just the air around us.
Sounds pretty futuristic, doesn't it? Straight out of science fiction.
It really does. But, this isn't just some far-off fantasy anymore. The whole world of energy, how we store it, how we use it, it's changing incredibly fast.
Breathtakingly fast, yeah.
And some of the most, innovative ideas coming out now are surprisingly gravitational.
That's a fascinating angle.
Okay, so let's unpack this. We've got a great stack of sources today, and we're going to pull back the curtain on our energy habits, our footprint.
And look at some of these incredible, sometimes frankly shocking ways we're trying to store and use power.
Exactly. So this is your deep dive today. We're calling it Unplugging the Future. We'll uncover hidden waste, explore these mind-bending solutions like gravity batteries.
And even cards that could power your house.
Right. And we'll also confront some surprising, maybe uncomfortable challenges ahead as we try to move towards sustainability. Get ready for some aha moments.
Definitely. Facts that might just make you rethink how you plug things in every day.
So where do we start?
Well, this deep dive couldn't be more crucial, really. The big challenge globally is pretty clear, isn't it?
Reliable, clean energy.
Exactly. How do we get clean, reliable power when sources like solar and wind? Well, they're intermittent by nature.
The sun sets, the wind stops blowing.
Precisely. And that variability makes energy storage not just important, but absolutely critical, foundational, really.
And you can't talk storage without talking consumption first.
You really have to. And it's quite striking when you look at the figures. Developed nations consume a disproportionate amount.
Like the U.S.
Like the U.S., yeah.
Yeah.
In 2021, Americans were about, 4.3% of the global population?
Something like that.
But accounted for roughly 17% of worldwide primary energy use. And some reports push that number even higher, maybe closer to 25%.
Wow. 17, maybe 25%. From just over 4% of the people. That's genuinely eye-opening.
It is. It puts our collective energy footprint into really stark perspective, doesn't it?
It absolutely does.
And this high per capita energy use, it translates directly into, significant global emissions, resource depletion. It's all connected.
And shifting away isn't simple.
Not at all. The complexity isn't just finding new sources, it's changing how we actually use power. Think about it, over 80% of the energy used in most American homes still relies on fossil fuels.
80%, that's deeply entrenched.
It is, so untangling that.
Yeah.
It takes systemic shifts. It's more than just building more solar farms,
Okay, here's where it gets really interesting for me personally, and maybe a bit subtly shocking for a lot of us listening. This idea of phantom power. I have to admit, I used to leave everything plugged in. Chargers, TVs, computers.
Most people do, I think.
Yeah. It wasn't until I actually started measuring it, with one of those little gadgets, I realized how much these off devices were still sipping power.
The vampire load.
Did you know that over 75%, 3/4 of the electricity consumed by home electronics is actually used while they're turned off, but still plugged in?
It's an incredible statistic, isn't it?
Yeah.
A subtle, pervasive drain that just goes completely unnoticed most of the time.
It really does.
And it's this hidden energy drain that, when you add it all up across millions of homes, puts significant and, frankly, completely unnecessary stress on the grid.
Like lots of tiny leaks making a flood.
Exactly. This constant low-level draw means our baseline demand is always higher than it needs to be, which in turn makes integrating those intermittent renewables even harder.
Right, because the grid has to supply that phantom load plus everything else.
Precisely. But the profound insight here is that tackling this isn't just about saving a few pennies on your electric bill, though it does that too.
It's bigger than that.
Much bigger. It's a readily available opportunity for significant energy conservation, something you, the listener, have immediate power to address. Just unplugging things using smart power strips.
Imagine the cumulative impact if everyone actually did it.
It would be substantial. A real immediate way to reduce grid stress.
Okay, so phantom power. That's a hidden problem right there in our walls. Let's pivot to some of these truly fascinating, almost sci-fi solutions for the bigger grid storage problem.
Right. Let's talk about storing the big power.
Gravity batteries. I mean, the name itself, one of the main players here is a company called Energy Vault.
Yes, I've been following their work.
When you see pictures or videos of their system, It honestly looks like some kind of colossal metallic insect, this giant multi-armed crane lifting and stacking huge blocks.
35 metric ton composite blocks, yeah. It's visually very striking.
It sounds like something from a futuristic building site. How on earth does lifting blocks store energy?
Well, the mechanics are remarkably simple at their core. And incredibly effective. When you have lots of cheap renewable energy, say midday sun, windy afternoon, you use that excess power to run motors that hoist these super heavy blocks way up high.
Storing potential energy, like stretching a rubber band, but heavier.
Exactly. You're converting electrical energy into gravitational potential energy. Then later, when demand spikes or the sun goes down or the wind drops,
you lower the blocks.
Precisely. You lower them in a controlled way. And as they descend, those same motors operate in reverse. They act as generators, feeding electricity back into the grid.
A giant, super efficient mechanical battery.
That's a good way to put it.
Conceptually, that clicks. But, given the sheer scale of energy we need, how practical is this for truly large-scale use? And what about efficiency? Surely you lose some energy in the lifting and lowering.
Good questions. Efficiency is key. Absolutely. Energy Vault system boasts a round-trip efficiency of over 80%.
80%, that's pretty good, isn't it? Competitive with other storage.
Very competitive, yes. Especially for longer duration storage. And here's another huge plus. Longevity. These systems are designed for a minimum operational life of 35 years or more.
35 years? Why?
And crucially, unlike chemical batteries, the storage capacity doesn't degrade over time. Doesn't matter how many times you lift and lower those blocks.
And degradation, that's a big deal compared to lithium-ion.
A very big deal. It means a lower long-term cost of storage, greater reliability over decades.
Yeah.
And you asked about scale. Their EVXC platform is designed specifically for utility scale needs. It can reach multi-gigawatt-hour capacities.
So really big installations.
Yes. And one more vital point, safety.
Yeah.
There are no electrochemical reactions involved, zero fire risk, which is a significant concern with some large-scale battery chemistries.
Okay, that makes sense. No chemicals, no fire. Here's another thing that jumped out at me from the sources, and it's genuinely surprising.
What's that?
While Energy Vault is Swiss-based, the country that's really running with this tech, deploying it rapidly, is China.
Yes, that's right. They've been moving very fast.
In 2023, they got a 25-megawatt, 100-megawatt-hour Energy Vault system in Rudong, fully connected to the grid. Made it the world's first commercial utility-scale non-pumped hydrogravity storage system.
A major milestone.
And it's not just a one-off. They already have 9 of these EVX systems underway in China, totaling, get this, 3.7 gigawatt hours of storage capacity.
That's a massive amount of gravity storage being built very quickly.
Why China? Why are they jumping on this so fast?
Well, this rapid adoption isn't really accidental. It's a direct result of their national energy policies.
Policy driving tech.
Exactly. China actually mandates that new renewable energy plants must integrate energy storage equivalent to 20% of their generation capacity.
20% storage mandate.
And typically for a duration of 2 to 4 hours. So the fascinating thing here is seeing how direct top-down policy can accelerate these nascent technologies much, much faster than just relying on market forces alone.
It shows a clear national strategy, a commitment to building out storage infrastructure.
Absolutely. It's quite a contrast sometimes.
So gravity batteries, super innovative, part of the solution, but just one piece of this massive puzzle, right? What else is out there in the world of long-duration energy storage? LDES, they call it.
Right, LDES. Because storing power for a few hours is one thing, but storing it for days, weeks, maybe even seasons, that's the ultimate goal for a truly resilient, renewable grid.
That's the holy grail, isn't it?
It kind of is. And the U.S. Department of Energy recognizes this. They launched their Storage Shot initiative back in 2021.
Storage Shot. What's the target?
The aim is a 90% cost reduction by 2030 for technologies that can store energy for 10 hours or more.
90% cost cut. That's ambitious.
Very. It underscores that while the science for many LDES techs is proven, it's really the economics that cost. That's the main barrier right now.
So what's the most common LDES tech we have today?
By far the most mature solution is pumped storage hydroelectricity, PSH.
Pumping water uphill.
Essentially, yes. It accounts for something like 95% of all active grid storage globally. It's elegantly simple. Use cheap electricity, often overnight, to pump water from a lower reservoir to an upper one.
Storing potential energy again, like the gravity blocks.
Exactly. Then, when demand is high and prices are up, you let the water flow back down through turbines, generating electricity.
How efficient is that?
typically around 70–80% round-trip efficiency. And it's a proven, reliable technology. The U.S. actually has plans for 67 new PSH projects to help meet its net zero goals.
67 new projects. That's a lot of water moving around. But it needs specific geography, right? Hills, reservoirs.
It does. That's one limitation. Which brings us to other options. What about systems that don't need massive elevation changes? Maybe using air.
Compressed air energy storage, CAES.
That's the one. CAES stores energy by compressing air, usually into large underground caverns, salt domes, depleted gas fields, aquifers.
And then you let the air out to spin a turbine.
Basically, yes. The first big utility-scale plant in Huntorf, Germany, has actually been running since 1978.
Wow, since the 70s.
Yeah. And modern systems, especially adiabatic CAEs, are even cleverer. They capture the heat generated during compression.
Which is usually wasted energy.
Right. They store that heat and then use it to reheat the air when it expands back out. This boosts efficiency significantly, pushing it over 70%.
Okay, so we have gravity, water, air. What else? I hear a lot about different kinds of batteries.
Definitely. Beyond lithium-ion, there are flow batteries. These are really interesting. They store energy in liquid electrolytes held in external tanks.
Liquids in tanks, how does that help?
The key advantage is decoupling energy and power. You can make the tanks bigger to store more energy without changing the power output, or increase the power stack without changing the energy capacity.
Ah, so you can scale energy and power independently, like having a huge fuel tank separate from the engine size.
Precisely. That makes them incredibly flexible for different grid needs. And the market for them is growing fast, projected to hit maybe $1.4 billion by 2030.
And I've heard whispers of even more sort of experimental ideas using liquid air or molten salt.
You have. There's liquid air energy storage, LDES, which cools air until it liquefies, stores it, then lets it expand to drive turbines. There's thermal energy storage, TES, often using molten salts to store heat at very high temperatures.
Flywheels too, right? For short bursts.
High-speed flywheels, yes. Good for short duration, high power needs, like frequency regulation.
So this brings up a really important question, or maybe a takeaway.
Which is?
It's becoming crystal clear that no single storage solution is going to be the magic bullet. There's no one-size-fits-all answer.
We need a mix.
Exactly. A resilient, reliable grid is going to need a whole portfolio of storage technologies. Different solutions optimized for different needs, different locations, different durations from seconds to seasons. It's about building a robust, diverse ecosystem, not picking one winner.
That makes a lot of sense. A whole toolkit. Okay, so we got all these exciting technologies bubbling up. But what does this massive shift actually mean for the planet?
The green footprint question. Yeah, because it's tempting to think green tech equals zero impact. But it's not that simple, is it? This is maybe another one of those nuanced, potentially shocking counterpoints.
It's absolutely crucial we look at this with eyes wide open. We need a holistic perspective, the full life cycle. Take the lithium-ion batteries powering EVs and grid storage now.
Right. Everyone talks about lithium, cobalt.
Exactly. Producing them involves extracting materials like lithium, cobalt, nickel, and that mining activity can lead to water pollution, land degradation, social issues. It's not impact-free.
Okay, that's known. But is there something more startling?
Well, here's a stark example focusing on a more common material.
Yeah.
Copper. An electric vehicle needs roughly 75 kilograms of copper.
75 kilos. How does that compare?
That's about 3 times more copper than a conventional gasoline car.
3 times more copper per EV.
Okay, now scale that up. Some estimates suggest that just one generation of renewable energy technologies, wind, solar, EVs, grid upgrades, could require something like 4.5 billion tons of copper.
4.5 billion tons. That sounds like an astronomical amount.
It is. Now, here's the truly startling part. Current known global copper reserves are estimated at only around 880 million tons.
Wait, we might need 4.5 billion tons, but we only have reserves of less than 1 billion tons.
That's the discrepancy highlighted in some analyses. It forces us to confront a fundamental, almost terrifying paradox, doesn't it?
Our green future seems to demand an unprecedented explosion in mining and extraction.
If we connect this to the bigger picture.
Yeah.
It implies a massive increase in mining globally, with all the potential consequences: destroyed landscapes, contaminated watersheds, resource conflicts.
And it's not just batteries, right? Even those cleaner LDES options have impacts.
They do. Large-scale pumped hydro storage can alter habitats, affect river flows.
Yep.
Building large underground caverns for CS can have its own footprint, potentially releasing greenhouse gases during construction.
So the deep insight here is Renewable or clean doesn't automatically mean zero environmental cost.
Not at all. While these technologies offer immense advantages over burning fossil fuels, we absolutely must focus on sustainable production methods, radically increasing recycling rates for all these materials and minimizing the localized impacts of extraction and construction.
We need to innovate our way out of this material bottleneck, maybe, or fundamentally rethink how much stuff we consume.
That's the multi-trillion-dollar question for the coming decades, isn't it? It's a huge challenge intertwined with the energy transition.
A sobering but really necessary perspective. Okay, let's shift gears slightly, though it's all connected. Electric vehicles.
EVs, definitely part of the picture.
The global shift seems to be accelerating incredibly fast. Projections show nearly 22 million EV sales globally in 2025 alone.
The growth curve is steep.
And China's dominance here is just undeniable. They account for nearly 2/3 of all global EV sales.
They're the giant in the market, no question.
So what about the U.S.?
Well, EV adoption is growing in the U.S. We have about 4.09 million EVs on American roads as of early 2024, so progress. But here's a recent and quite shocking change in the outlook.
Oh, what's happened?
Bloomberg and EF, who are major analysts in the space, they've actually downwardly revised their forecast for the U.S. market for the first time ever.
Downwardly revised? By how much?
By 14 million cumulative EV sales by 2030.
14 million fewer EVs sold in the U.S. by 2030 than previously expected. That's a huge revision. Kind of alarming, actually.
It is significant.
Why? What's causing the slowdown or expected slowdown in the U.S. specifically, especially when the global trend is still shooting up?
Well, the analysis points directly to policy changes or the uncertainty around policy.
Policy again? Like what?
Things like the rollback of federal fuel economy standards, the planned phase-out of the main EV tax credit, and the ongoing debate about California's ability to set its own stricter air quality standards, which often drives innovation.
So wavering government support is putting the brakes on. It really shows how fragile these market shifts can be without consistent backing, doesn't it?
It really does. Governmental signals, or lack thereof, have a huge and immediate impact on investment, manufacturing plans, and ultimately consumer confidence and adoption.
And infrastructure must play a role too, charging stations.
Absolutely. We can't ignore the, frankly, slow rollout of federally funded charging infrastructure. As of April 2025, only 384 federally funded chargers were actually open and operational.
384 across the whole country. That seems tiny.
It's a very slow start. And that kind of infrastructure lag definitely impacts people's willingness to switch to EVs. Range anxiety is real if charging isn't convenient and reliable.
Okay, so challenges remain. But let's talk about something potentially transformative using those EVs. Vehicle-to-grid. V2G technology.
V2G, yes. This is incredibly exciting.
It sounds like it could turn EVs into more than just cars. They could become, active parts of the power grid?
That's exactly the concept. What's truly fascinating here is the potential to transform millions of individual vehicles parked cars, basically into a vast, flexible, mobile energy storage network.
Mobile storage? How does that work?
Well, EVs obviously draw power from the grid to charge their batteries. VDG enables them to do the reverse, send unused energy back to the grid from their batteries when needed.
So my car battery could help power my neighbor's house during peak demand?
In theory, yes. During peak hours, or when renewable generation dips, fleets of VDG-enabled EVs could discharge a small amount of their stored energy back to the grid, helping to stabilize the whole system.
Wow. That creates incredible possibilities for grid balancing, demand response, like turning millions of cars into a giant distributed power plant.
That's the vision. A vast, flexible resource that's already sitting in driveways and parking lots most of the time.
The potential of V2G is genuinely exciting, but this vision of a smarter two-way grid bumps right up against a pretty stark reality, doesn't it?
You mean the state of the existing grid?
Yeah. America's aging electrical infrastructure. I was reading Gretchen Bake's book, The Grid.
A fantastic, if somewhat alarming, read.
She argues quite persuasively that the more we invest in intermittent green energy, the more fragile our underlying grid actually becomes.
Because it wasn't designed for it.
Exactly. She describes the grid as, quote, worn down, patched up, and every hoped-for improvement is expensive and bureaucratically bemired. It sounds like trying to run bullet trains on rickety 100-year-old tracks.
She hits on a absolutely critical point. The grid we have today was designed, fundamentally, for a one-way flow of power, from large centralized fossil fuel or nuclear plants outwards to consumers, predictable, controllable.
But renewables are different, distributed, intermittent.
Exactly. And adding millions of EVs charging, maybe discharging with V2G, it's a completely different architectural challenge. This raises a really important question, or maybe a warning.
Which is?
Investing billions solely in renewable generation isn't enough. Not even close.
You need to upgrade the wires, too.
Massively. We need significant, costly, complex upgrades to the transmission and distribution infrastructure. The poles, the wires, the substations, the control systems, the whole network.
So connecting this to the bigger picture, without a fundamental reimagination of the grid, as Bake puts it.
The full potential of all this renewable energy and storage tech might just remain unrealized. We're talking about a complete overhaul, a rethinking of its architecture and operation, not just bolting new bits onto an old system.
A huge undertaking, thinking about these massive, almost overwhelming challenges. It actually makes me think back to some other monumental big builds in American history.
Like what?
Like the Erie Canal back in the early 19th century. People thought it was insane. Critics called it Clinton's ditch. Even Thomas Jefferson said building it was little short of madness.
And yet?
And yet they built it. It transformed New York City into the country's commercial powerhouse. It set precedents for how to finance huge infrastructure projects.
That's a great example. Or the Transcontinental Railroad in the mid-19th century.
Right. A brutal, incredibly difficult 7-year project. But it slashed cross-country travel from months down to about a week. Completely changed the nation.
These historical projects, they offer some really crucial lessons for our current energy transition, don't they?
What stands out to you?
Well, first, ambition pays off. Even when faced with daunting challenges and widespread skepticism, bold vision can succeed. Second, innovation and adaptation are constant.
How so?
The Erie Canal, a marvel of its time, was eventually made largely obsolete by the railroads, which, in turn, continued to evolve. It tells us that our current energy tech, as amazing as it seems now, will also keep evolving rapidly.
We shouldn't assume today's solutions are the final word.
Definitely not. And third, the sheer scale of investment and commitment required.
Yeah, these weren't cheap or easy. They needed immense public and private capital, long-term vision, overcoming huge technical and logistical hurdles.
Absolutely. Bill Gates talks about this, doesn't he? The urgent need for big breakthroughs, especially in areas like long-duration storage and better high-voltage transmission lines. He calls them energy miracles.
We need that kind of ambition and investment again today, perhaps on an even bigger scale.
We do. These historical projects powerfully illustrate that kind of long-term vision, the blend of public and private funding, and just the sheer grit needed to overcome obstacles, the challenge of financing it all and maintaining the political will. That's as critical now as it was 200 years ago.
Okay. So we've covered a lot of ground in this deep dive. We've journeyed through this fascinating, sometimes really startling world of energy.
From the subtle drain of phantom power in our own homes,
to the truly exciting promise of things like gravity batteries, liquid air systems, flow batteries, and EVs that might one day literally power our homes through V2G.
We've touched on the critical, complex need for long-duration storage. We acknowledged how policy, like in China, can really drive deployment.
And we've also had to confront some uncomfortable truths, haven't we? The surprising material demands of green tech, that copper statistic.
And the profound challenge posed by our aging electrical grid. It's not a simple picture.
Not at all.
And I think what's really crucial to grasp is how deeply interconnected energy systems are with everything else. Economic development, social behavior, even geopolitics, and power dynamics.
It's not just an engineering problem.
Far from it. Solving this complex challenge needs brilliant science and engineering, yes, but it also demands bold policy innovation, significant economic restructuring, maybe even fundamental shifts in collective human behavior. It's a truly multifaceted endeavor.
Let's end maybe with a thought that puts all our current efforts into an even grander perspective.
Okay.
To really grasp the scale of human energy use and the potential ahead, we can look at something called the Kardashev scale. Are you familiar with it?
Vaguely. It ranks civilizations based on energy use.
Right. Exactly. It measures a civilization's technological advancement by how much energy it can harness. A Type I civilization on this scale is one that can access and store all the energy available on its home planet.
All the solar energy hitting Earth, geothermal, tidal, everything.
Everything. Now consider this. Humanity currently harnesses around 4 times 10 to the 12 watts of power globally.
Okay.
A theoretical Type I civilization could harness around 2 times 10 to the 17 watts.
Wow. 10 to the 12 versus 10 to the 17.
That's a staggering 50,000-fold increase.
50,000 times more energy than we use today. This raises a pretty profound question, doesn't it?
It really does. That immense gap between where we are now and a theoretical Type I civilization, it just highlights the vast, almost unimaginable, untapped potential for growth and innovation that still lies ahead of us.
So our current energy challenges, as daunting as they feel right now, they could be seen as just the very early steps, the initial hurdles in a much grander evolutionary journey for human civilization's relationship with energy. It frames it as unlocking truly planetary scale power eventually.
So ultimately, the future of energy, it isn't just about fancier gadgets or bigger batteries, is it?
Not fundamentally. It's about reimagining humanity's entire relationship with power itself.
Building a grid, an energy system that's not only resilient and efficient,
but also equitable, accessible, and truly sustainable for generations, centuries, maybe millennia to come.
After this deep dive today, thinking about phantom power, gravity, copper, the grid, even Type I civilizations, what stands out most to you about how we power our world and where we might be headed?